Hello students, welcome to ALPHORES e-learning channel. This is K. Nageshwar Rao, your physics faculty. Today we are about to deal with session number 96. It is from current electricity chapter, second year, Neet. Okay, let us see what we can do. In the previous session, we have discussed about Wheatstone bridge principle and a few problems we have seen. We have dealt with unbalanced bridge as well. Okay, now let us continue. I will continue with one of the application of Wheatstone bridge. Instead of it's okay if you call it as a practical way of realizing Wheatstone bridge. So Wheatstone bridge, in the sense, what you know is, you know a circuit something like this, isn't it? P, Q, R, S, like that. Four resistors are arranged. One galvanometer is arranged here. When the bridge is balanced in the sense, potential at point B, potential at point D both are same. So it means there is no potential difference. If there is no any potential difference, current passing through the galvanometer will be 0. So IC value will be 0. So in that case, what was our conclusion earlier in the previous session? P by Q is equal to R by S. That ratio is possible. So this is what Wheatstone bridge is. Practically, if you wanted to realize Wheatstone bridge, what you can do is you can deal with Mater bridge. Mater bridge facilitates the possibility of realizing Wheatstone bridge practically. So let us see how does a Mater bridge looks like. So this is what a Mater bridge is. A Mater bridge has a copper strip arrangement. This L-shaped one is copper strip arrangement. This straight strip is also copper strip only. This L-shaped strip is also copper strip, and all these things are arranged on a wooden platform. And between A and B, if you say, there is a wire, red color wire, that is of length equal to 1 meter. So that's how the name is justified. Mater bridge will take 1 meter length of the wire between these 2 points A and B. So here one gap is there between this strip and this strip, that is called as a left gap, and here another gap is there between this strip and between this strip. So this gap is called as usually right gap. So left gap, right gap. So in left gap, resistance box is arranged. In the right gap, one resistor is arranged. Okay, so this J is called as jockey. Jockey is a kind of it appears like a cylindrical small arrangement, cylindrical a pen kind of thing. You can assume like that. That jockey is used for tapping on this wire. When we do tapping, what happens? We see deflections in the galvanometer. So here this jockey is connected to what? Galvanometer, and this galvanometer is directly connected to this strip. You can use HR, high resistance box can be used, or without that also you can perform the experiment. Let us say a high resistance box is also connected here. So from the jockey it is connected to galvanometer, and again HR, and from here it is connected to this point, to this blue dot. Now, just now I said Mater bridge is something where you can practically realize Wheatstone bridge. Now, do we see Wheatstone bridge here in Mater bridge or not? Let us try to understand that. Whatever this P is there, that P is this resistance box in Mater bridge. Whatever this Q is there, that Q is this resistance in the right gap. Whatever this R is there, that is resistance of length of this length of wire, this part of the wire. This is the jockey. This jockey has divided this wire into two parts. Okay, they can be of same length, they can be of different length. It all depends on where you are getting balancing point in the sense where the bridge is getting balanced. So to the left of jockey, whatever length of the wire is there, and that length of the wire offers some resistance, that is what our R is. And to the right of jockey, whatever length of the wire is there, that also offers some resistance, that is termed as S. This is that S. Okay, so let us try to understand this one a little bit more, Mater bridge, okay, regarding its arrangement and all. Okay, so this is how in laboratory Mater bridge looks like. Wooden platform, these are copper strips, this is left gap, this is right gap. Okay, here one resistance box is arranged, here unknown resistance is arranged, and see here, this is the scale. This is the scale. On this scale, if you see white color string is there, that is of 1 meter length wire. Okay, 1 meter length wire. And this object, whatever this object is there, that is called as jockey. That is called as jockey. Okay, and this jockey is connected to galvanometer. This is galvanometer, and galvanometer is connected here. Okay, so here let me go back to the previous slide. This part you have seen, it's here. Q, it's here. R, it's here, this length of the wire. S, this length of the wire is nothing but S. And this arrangement is what? Whatever connection is there between point B and D, between point B and D, that is this one. Okay, so I hope you are able to visualize Wheatstone bridge here. Okay, let us proceed with further discussion. Let us have a close look at all the elements. So the top view of meter bridge. These are copper strips. This is left gap. This is right gap. This is a meter scale, and on that wire is arranged whose length is equal to 1 meter. And this is what resistance box is, which is arranged in left gap. And unknown resistance. See here, a small wire is connected here. That is what unknown resistance, and that can be calculated with the help of Wheatstone bridge principle. And this is the galvanometer. See, this is the closure view of jockey. This is how a jockey appears like. So with the jockey, what do? We tap on the wire. Tapping is different from pressing. If you press the wire, what happens? The wire gets damaged. When the wire, this wire, when it gets damaged, it will have a non-uniform cross-section area. If cross-section area is different, that can influence the resistance. We know that resistance is inversely proportional to cross-sectional area. So we are supposed to handle this jockey in a very soft way. We are not supposed to press very hard on this wire. Okay, so this is the galvanometer. If galvanometer is pointing 0, it means the bridge is balanced. It means there is no current pass through the galvanometer. If any current passes through the galvanometer, this needle will deflect towards right or left depending upon direction of the current. Okay, so let us now try to understand how does this meter bridge principle, principles, Wheatstone's bridge principle can be applied to meter bridge, and theory related to meter bridge can be evaluated. So this is what the conclusion is. When the bridge is balanced, what do we write? We write it as P by Q is equal to R by S. So this is our meter bridge. We have already seen how Wheatstone bridge can be visualized in meter bridge. Okay, so this is what P, and this is Q, and this length of the wire, whatever resistance it offers, that is R. The other length of the wire, whatever resistance it offers, that is S. Okay, and this is our galvanometer setup connected to the jockey. Now let us say at this point the bridge is balanced. Bridge is balanced in the sense when you have tapped with the jockey here, the galvanometer, let us say it is showing null deflection. If it is showing null deflection, what does it mean? There is no current passing through this one. It means the bridge is balanced. It means P by Q is equal to R by S can be, can be used here. So what is P here? Y is P. What is Q? X. So in place of P by Q, what you can write? Y by X can be written. What about R by S? Here lengths are there, L1 and L2. Resistances were not given. Resistance values are not given. But no problem. We know that resistance is directly proportional to length. Okay. So resistance of this part of wire is directly proportional to L1. The resistance of the other part of the wire is directly proportional to L2. So the ratio between R and S can be written as L1 by L2 because R is directly proportional to length, or resistance directly proportional to length. So in place of R by S, what you can write here directly, L1 by L2 can be written. Okay. So this L1 is here in the numerator. This L2 can be replaced with 100 minus L1 because total length of the wire is 100 centimeters, isn't it? So if this part of the wire is L1, what will be this part's length? 100 centimeters minus L1. L2 is equal to 100 minus L1. So that's what we have replaced. And in most of the cases when we deal with the numerical problems, this is what we use. Y by X equal to L1 by 100 minus L1. Okay. Now let us draw a few conclusions of meter bridge. These are few conclusions. What is the first conclusion? If resistance in the left gap increases or resistance in the right gap decreases, balancing point shifts towards right side. So if resistance in the left gap increases, what is happening to the balancing point? It is shifting towards right side. Let us see that whether it is possible or not. So what is happening here? Resistance in the left gap is increased. So Y value is increased. If Y value is increased, what will happen to Y by X? Y by X increases. If Y by X increases, this L1 by 100 minus L1 also increases, isn't it? This is increasing in the sense L1 is increasing, numerator is increasing. So if L1 is increasing, what does it mean? L1 is increasing in the sense earlier when the jockey is tapped here, this is where you have found balancing point. Now L1 has increased in the sense balancing point will be somewhere here, isn't it? Somewhere here on the right side of the balancing point. Okay, so the length of length L1 increases. It shifts towards right side. The balancing point shifts towards right side. So that's what it was mentioned in the conclusions. What was the first conclusion? If resistance in the left gap increases or resistance in the right gap decreases, either way, let us see. If resistance in the right gap decreases, x value is decreasing. If x is decreasing, what happens to this y by x? Y by x increases. If y by x increases, this value increases. This value is increasing in the sense L1 is increasing. L1 is increasing in the sense balancing point is not here, it will be somewhere here. So the balancing point has shifted to the right side of the earlier balancing point. Okay, that's what the first conclusion was. And see the second conclusion, if resistance in the left gap decreases or resistance in the right gap increases, balancing point shifts towards left, opposite to the first conclusion. Okay, and the third one is, if a centimeter, b centimeter are the end corrections at a and b, then r by x is equal to L1 plus a by L2 plus b. For example, here the wire, whatever this 100 centimeter length of the wire is there, that is connected to these copper strips. Now through these copper strips also current is flowing, right? So from here to here also current flows, isn't it? So, and if at all, if any extra wire is used, that will be winded here to the whatever screw arrangement is there, or some kind of metal knob arrangement is there, to that we'll wind it up. So some extra length contribution will be there. So that's what we are calling it as end correction. That's what we are calling it as end correction. So if a centimeter and b centimeter are the end corrections of at a and b, then r by x can be written as, earlier without considering end corrections, we have written it as L1 by L2. If extra length, whatever possible length is there, if that is also considered, on the left side, okay, starting from a, what will be the length? L1 plus a. On the right side, starting from b, the length will be L2 plus b. Okay, so this is one conclusion. The other one is, meter bridge is more sensitive if L1 is equal to 50 centimeters. So it is more sensible when L1 is 50 centimeters. Sensibility in the sense, I told you in the previous session also, very quickly there will be response from the circuit. In the galvanometer, you will be able to see the deflection very quickly. Okay, provided if L1 is 50 centimeters. Okay, now, right. The resistance of copper strip is called end correction. Yeah, just now I told you. So whatever resistance is offered by the copper strip here, this copper strip and this copper strip, that is called as end correction. Okay, so this is about meter bridge. Now let us try to solve one problem connected with the meter bridge. The question is, in a meter bridge, the null point is found at a distance of 40 centimeters from A. If a resistance of 12 ohms is connected in parallel with S, the null point occurs at 50 centimeters from A. Determine the values of R and S. Let us see the circuit once. So this is the circuit. What was said? In a meter bridge, the null point is found at a distance of 40 centimeters from A. Maybe somewhere here. From point A to somewhere here, you have found a balancing point at a distance equal to 40 centimeter. Okay, for a particular value of R and S. If a resistance of 12 ohm is connected in parallel with S, so it means, see, 12 ohms resistance is not there, previously. Only R and S are present. At that time, what is the balancing point? Balancing point is at a distance of 40 centimeters, or balancing length is 40 centimeters. Remember children, I am telling you again, balancing length is measured from point A. Okay, like this. From point A, you will be measuring balancing length. So how much is that balancing length when R and S alone were taken? 40 centimeters is the balance length. Now what was done? A resistance of 12 ohms is connected in parallel with S. So like this, 12 ohm resistor is connected in parallel with S. Now the null point occurs at 50 centimeters. So earlier it was at 40, now it is at 50. Okay, from A. Determine the values of R and S. So we don't know what this R is, we don't know what this S is, some data is given. Okay, we have to find out R and S values. Okay, so this is what we use when the bridge is balanced. Y by X is equal to L1 by 100 minus L1. So here in place of Y, what do we have? R is there. In place of X, what do we have? S is present. So Y by X can be replaced with R by S. And when R and S were alone taken, what is L1 value? 40 centimeters. So here in place of L1, what you can write? 40. And L2 will be how much? 100 minus L1. Because this total length is 100, no? So if at a distance of 40 centimeters a balancing point is obtained, L1 can be taken as 40. The other part of the length will be how much? It's 60, isn't it? So 100 minus 40, 60. So 40 by 60 is 2 by 3. So we have got R by S as 2 by 3. And what was the next condition? If resistance of 12 ohms is connected in parallel with S, the null point occurs at 50 centimeters from A. Okay, So now I'll assume that 12 ohms resistance is connected parallel to S. So in the parallel combination, what will be the effective resistance? That will be replaced in place of X now. Okay, in place of Y, the same R will be replaced. So in place of Y, I have replaced R. In place of X, I have replaced with the effective resistance of the parallel combination. Effective resistance of the parallel combination is what? If you are having two resistors, R1, R2 by R1 plus R2. R1 is 12, R2 is S by R1 plus R2, which is equal to, corresponding to this 12 ohm resistor, being parallel to S, what was the null point? 50 centimeters. Okay, so if L1 is taken as 50, 100 minus 50 is again 50. So 50 by 50, you will have 1. So from this, R can be written as, you have to multiply to this one, cross multiplication, then you will have R is equal to 12S by 12 plus S. Okay, so now I can replace this R in this equation. Okay, if this R is replaced with 12S by 12 plus S, this is what we'll get, 12S by 12 plus S into S, whatever this denominator S is there, that also appears here, is equal to how much? 2 by 3. 2 by 3. Now we can simplify this to find out S value. So S value comes out to be as 6 ohms. Once you obtain S value, you can substitute here and you can obtain value of capital R. How much is that? It comes out to be as 4 ohms. So that's how this problem can be handled. Let us see one more question. A resistance of 2 ohms is connected across one gap of a meter bridge. Okay, one gap. It was not mentioned whether it is left or right. I'll consider that this 2 ohm resistance is connected in left gap. The length of the wire is 100 centimeters. This is known to us in a meter bridge. The length of the wire will be 100 centimeters. And an unknown resistance greater than 2 ohms is connected across the other gap. So across the other gap, a unknown resistance is connected. Unknown resistance, and whose resistance is not mentioned, but it was said that that resistor's resistance value is greater than 2 ohms. In the left gap already we were having 2 ohms resistance, and in the right gap whatever resistance is there, that is more than 2 ohms. That's what information he has given. Okay, when these resistances are interchanged, okay, so from right gap resistor was taken and it is placed in left gap, and from left gap resistance is taken and it is placed in the right gap, like that, interchanged. When they were interchanged, the balance point shifts by 20 centimeters. So this question, it has a lot of information. The balance point shifts by 20 centimeters. It was not mentioned whether it is shifting towards left or towards right. We have to find out. With our knowledge of meter bridge, we have to find out whether this shift is towards left or towards right. Now, neglecting any corrections, end corrections, he meant to say that, end corrections, neglecting any corrections, the unknown resistance is, so whatever this unknown resistance, which is greater than 2 ohms, what is that unknown resistance? We have to find out that. So let us see how it can be solved. So this is the circuit diagram. Let us say this R1 is equal to 2 ohms and this R2 is greater than 2 ohms. Okay, let us say somewhere here balancing point is obtained. Okay, it's let us say L is the balancing length. The other part of the length will be equal to 100 minus L. So this is the equation, when the bridge is balanced, when the meter bridge is balanced, this is what equation we will be using. R1 by R2 is equal to L1 by 100 minus L1. So this R1 is 2 ohms and R2 is what? Some unknown resistance whose value is greater than 2. So R2 is greater than R1. This is very important point. You have to remember this. R2 is greater than R1. Okay. It means R1 by R2 is less than 1. Less than 1. Okay. So now I have assumed that R1 is 2. So R1 is replaced with 2. R2 I have assumed it as X. And this X is slightly greater than 2. And L1, it was mentioned that, here in the figure it is mentioned that balancing length is L. The other length will be 100 minus L. So L by 100 minus L. Now, for the other case, when their positions were switched, like R2 is placed here, R1 is placed here. What happens to the equation? It will be X by 2. X by 2. What is this X? X is greater than 2. So if X is greater than 2, this X by 2 value will be greater than 2 by X. This X by 2 is greater than 1. This 2 by X is less than 1 because X is greater than 2. Isn't it? So if that is the situation, if X by 2, when compared to this one, if X by 2 value increases, what does it mean? The balancing length, L value, in the case of what? Interchanging, in the case of interchanging, the balancing length increases. So if it increases, It was already said that in the question it shifts by 20 centimeters. Since we have identified that length increases after interchanging, so what will be the new balancing length? It will be L plus 20. Okay, so that's what I was talking about. We don't know whether it is L minus 20 or L plus 20, but from the given information we can identify that x by 2 value is more. It's more in the sense the numerator should be more. Numerator should be more in the sense earlier it was L, now it will be more than L. It should be more than L. It means it will be equal to L plus 20. If it is L plus 20 and if you subtract from 100, 100 minus L plus 20 is how much? 80 minus L. So now we have two equations and our job is very simple. We can solve for x. Okay, you can solve for x and it comes out to be as 3 ohms. So that's how we can find out what values of unknown resistances. Thank you, students. With this, I will close the session. In the next session also, we will deal with a few problems connected with the meter bridge. Okay, thank you.